Hello friends, welcome to a lecture series on matrix analysis with applications. So, this is the first lecture and this lecture deals with elementary row operations. So, what elementary row operations are and how it is applicable to solve linear system equations we will see in first few lectures. So, before stating what elementary row operations are, first we define binary operations. So, let G be a set. A binary operation on G is a function that assigns each ordered pair of elements of G an element of G. So, what does it mean? It means if G is a set, you take any two arbitrary element in that set, apply the operation given to you, and the resulting element, if it is also belongs to a same set, then we say that the operation is a binary operation. Like you take the set of natural numbers, okay, and you apply usual addition. So, we know that if we take any two arbitrary natural numbers and we apply usual addition operation usual addition on the natural numbers, then the resultant is also a natural number. That means the usual addition for the set of natural numbers is a binary operation. Similarly, if you take in set of integers here, okay, and you apply usual addition, you take any two integers, add them, the resultant is also an integer. That means the usual addition over the set of integers is a binary operation. Similarly, you take the set of rational numbers or the real numbers or complex numbers, under usual addition usual addition is a binary operation. Now, similarly, if you take the set of natural numbers, okay, and you take binary operation as usual multiplication, okay, if you take any two natural numbers, you multiply them, the resultant is also a natural number. That means the usual multiplication over the set of natural numbers is a binary operation. Okay. Similarly, set of integers, rational numbers, real numbers and complex numbers, the usual multiplication is the binary operation. Now, if you take a set of natural numbers, subtraction and divisions are not binary operations. Suppose you take two natural numbers, say 1 and 2. 1 minus 2 is equal to minus 1, which is not an integer. That means subtraction over set of natural numbers is not a binary operation. Similarly, if you take division, you say you take two natural numbers, say 2 and 3, you divide them 2 upon 3. So, 2 upon 3 is not a natural number. So, that means division is not a binary operation. So, that means binary operation is the operation which, when applying to any two elements of a set G, the resultant element must be in the same set, then that operation is called binary operation. Now, come to group. When we say that a set is a group under some binary operation, okay. So, let G be a set together with a binary operation that assigns to each ordered pair A comma B of the elements of G an element in G denoted by A into B or AB. Okay. We say G is a group under this operation if the following three properties are satisfied. Okay. First of all, the operation which we are defining on the set G is a binary operation. Binary operation means it satisfies closure property. That means you take any two arbitrary element on the set G, the resultant element is also in G. Okay. And what are the other three properties which a set G should satisfy to form a group? Number one, associativity. Associativity means you take any three arbitrary element A, B, C in G. If you take brackets in the first two elements or you take the bracket in the last two elements, the values are same. That is associativity. Okay. Then the identity. Identity means if there exists an element E, which is also called the identity in G, such that AE equal to EA equal to A for every A in G. Then the third property is inverse. Inverse means For each A in G, there is an element B in G called the inverse of A such that AB equal to BA equal to E. Okay. So, if these three property hold on a binary operation applied on G, then we say that the G under that binary operation is a group. So, what are the four properties which we have discussed? Number 1, the operation must be a binary operation. Number 2, associativity. Number 3, identity. Identity means you take any arbitrary element A in G, there exists E such that AE equals to EA equals to A for every A in G. Inverse means for any A in G, there exists an element B in G such that this result hold. Moreover, this group will be called an abelian group if it satisfy a commutative property also. That means AB equals to BA, AB equal to BA for all AB in G. Okay. So, let us discuss this by an example. Suppose you take a set of real numbers, okay, set of real numbers. Let us suppose denoted by capital R, okay, and under which binary operation it must be mentioned. The binary operation which we are defining here is suppose usual addition, okay. So, we know that usual addition on the set of real numbers, is a binary operation, because if you take any two elements A comma B belongs to R, then A plus B, if this is usual addition, if we are denoting by plus, then A plus B is also in R for all A B in R. So, that means this plus which is applying on the two elements A B in R is a binary operation. Okay. Now if we have to see that whether this set of real numbers under this binary operation forms a group or not. Okay. So, this is a binary operation. Now, we have to see the other three properties are satisfying or not. Number 1 property is associative property. So, associative property is obviously satisfied because addition always satisfied associativity. You take for all A B C in R, A plus B plus C is equals to A plus B plus C. You take bracket in the first two elements or you take bracket in the last two elements, resultant is same. Now, next is to see whether identity exists or not. You take any element A in R. Okay. Now, A plus E is equal to E plus A must be A for any A in R, and this implies E equal to 0, and 0 is in R. So, this belongs to R. That means, for any A in R, identity element is 0 which exists and belongs to the set of real numbers. The third property is inverse. You take any A in R, then A plus B plus is equal to B plus A should be equal to E, E is 0. So, this implies B is equal to minus A which also belongs to R. Suppose you want to find out the inverse of 2, 2 is a real number. So, inverse of 2 is minus 2 which is also in R. So, we have shown that all the properties are satisfied, that means this set R over the binary operation usual addition forms a group. Okay. Now, if we see the same set of real numbers, over multiplication. Okay. If we say same set of real numbers over usual multiplication, so we have to exclude 0 because inverse of 0 is not defined here. So, we are here to exclude 0. Okay. Now, if we are taking this set, the set of real numbers excluding 0 under usual multiplication, it forms a group. Usual multiplication is a binary operation, because if you take any two arbitrary element from the set, from this set say G, and multiply them, then the resultant is also a real number. So, it is a binary operation. Now, the first property associativity holds, because A into B into C is equals to A into B into C for all A B C in G. The second property is identity. You take any element in G, say A belongs to G, then A into E should be equals to E into A should be equals to A for all A in G, and this implies E equal to 1, which is in G. So, this means there exists an identity element in G. And third is inverse. If you take any A in G, so it is A into B should be equals to B into A should be equals to E, which is 1. So, this implies B is equals to 1 by A, which also belongs to G. Suppose you want to find out multiplicative inverse of 2. So, it is 1 by 2, which is in set of real numbers excluding 0. So, that means this set G under binary operation usual multiplication constitute a group. So, here are some examples. You see the set of integers Z, the set of rational numbers Q, the set of real numbers R are all groups under ordinary addition, usual addition. In each case, the identity element is 0 and the inverse of an element A is minus A. In fact, all these are abelian groups, because they satisfy a commutative property also. If you take the set of integers, you take A into B or B into A, resultant is same, the values are same. That means the set of integers in fact forms an abelian group. Similarly, set of rational numbers, set of real numbers also forms an abelian groups. Now, you take this set 1 minus 1 iota minus iota, okay. You take this set. Now, set is 1 minus 1 iota minus iota. We know that iota square is minus 1. And what is the binary operation? Under which binary operation we are seeing that it will forms a group or not? Under usual multiplication. We know that the usual multiplication is a binary operation for this G. Why it is binary operation? This you can easily see. You take 1 minus 1 iota minus iota, okay. You take 1 minus 1 iota minus iota. Now, you multiply 1 with 1 is 1, 1 with minus 1 is minus 1, 1 with iota is iota, this is minus iota, minus 1 with 1 is minus 1, then plus 1 minus iota, iota square is minus 1, okay, it is plus iota, okay. Iota with 1 is iota, it is minus iota, iota square is minus 1, minus iota square is 1, it is minus iota, it is plus iota, it is minus iota square is 1 and it is minus 1. Now, we have seen all the possible multiplication of the elements of G with itself, and we have seen that all the elements in this set are in G itself. That means, this usual multiplication on this set G is an binary operation. That is clear, because if you multiply any element of G with itself, okay, all the elements are in G itself. That means, usual multiplication on this G is a binary operation. So, first property is hold. Now, we have to see the associative property. So, associativity is always hold in multiplication, in usual multiplication is always satisfied. Then we have to see identity element, existence of identity element. If you take any A in G, then A into E should be equals to E into A should be E for all A in G. This implies E is equals to 1, which is in G. You see here, this is 1, which is in G. So, that means identity element also exists. which is in G. Now, the existence of inverse, if you see the existence of inverse, so you take any A in G, then for inverse AB should be equals to BA should be equals to E, which is 1. Then this implies B is equals to 1 by A. Okay. If you take the inverse of 1, inverse of 1 is 1 by 1, which is 1, which is in G. If you take inverse of minus 1 inverse is 1 upon minus 1, which is minus 1, is also in G. Inverse of iota, which is 1 upon iota, which is minus iota, it is also in G. And inverse of minus iota is 1 upon minus iota, which is iota, it is also in G. So, inverse of all the elements exist, okay. A identity element exists, associativity property holds. So, we say that this set G under this binary operation, I mean usual multiplication, constitute a group. Now, you set this, you take this set, the set S, which is set of all 2 cross 2 matrices whose determinant are not equal to 0. That means invertible matrices of order 2 cross 2. Now, if you take, so here binary operation which we are choosing is a usual multiplication, it forms a non-abelian group. Now, let us see how. So, we are taking all those 2 cross 2 matrices whose determinant are not equal to 0, okay. And what is the operation we are applying? Operation is usual multiplication. Okay. Now, you take any A comma B belongs to S. This means determinant of A is not equal to 0 and determinant of B is not equal to 0. Okay. If you take the multiplication of these two matrices A into B and take the determinant of AB is equal to determinant of A into determinant of B, which is also not equal to 0. This implies AB belongs to S. That means this usual multiplication forms a binary operation on this set S. Okay. Now, we have to see associativity. The matrices satisfy associative property, we already know that A B into C is same as A B C for all A B C in S. This is always satisfied in case of matrices. Now, existence of identity element. You take any A in S, A into some E should be equals to E into A should be A. So, this implies E is equals to I, and determinant of I is not equal to 0. So, this implies I also belongs to S. So, this guarantees the existence of identity element in S. Now, we have to see existence of inverse element. You take any A in S, then A B should be equals to B A should be equals to I, and this implies B is equals to A inverse. Now, inverse exists because determinant is not equal to 0, and since determinant is not equal to 0, then determinant of A inverse is also not equal to 0. Determinant of B will be what? Determinant of A inverse, and which is equals to 1 upon determinant of A, which is also not equal to 0 because from here determinant of A is not equal to 0, and this implies B belongs to S. So, we have shown the existence of inverse element also in S. So, hence we can say that this S constitute a group under usual multiplication. Okay. Now, it is a non-abelian group. Why non-abelian? Because if you multiply A into B or you multiply B into A, they need not be equal. A into A B, it need not be equal to B into A for all A B in S. Okay. So, it is a group, but it is not an abelian group. Okay. Now, the set of integers Z excluding 0 under ordinary multiplication is not a group, because if you can clearly see, if you identity element is there, identity element under multiplication is 1, but if you take element say 2, its inverse is 1 by 2, which is not in this set of integers excluding 0. Hence, it will not constitute a group. So, this is all about group. Now, we come to field and then we go to matrices. Okay. Now, what is a field? Let us see. Let us quickly see. A non-empty set F equipped with two binary operations, addition and multiplication, is said to be a field if it satisfies the following axioms for all A, B, C in F. Now, here in fields, instead of one binary operation, we are having two binary operations. The first binary operation we are denoting by addition. It may be any operation, but we are denoting it by addition, and the second binary operation we are denoting by multiplication. Now, the first property is commutativity holds of for addition and multiplication. That means A plus B should be equals to B plus A for all A, B in F, and A into B should be equals to B into A in case of both the binary operations, number 1. Number 2, associativity of addition and multiplication must hold. Okay. Existence of additive and multiplicative identities should exist, that is 0. We are denoting 0 as the additive identity and 1 as a multiplicative identity. So, 0 plus A should be A and 1 dot A should be A for all A in F. Then existence of additive and multiplicative inverses. So, here minus A is simply additive inverse of A and 1 by B is simply multiplicative inverse of B, where B is a non-zero element in F. Okay. And the distribution of multiplication over addition from right also and from left also, from left and from right, this must hold. So, what I want to say basically that in case of field, we are having two binary operations, one we are calling as addition, other we are calling as multiplication. So, F with respect to addition must be an abelian group, okay, and all non-zero element in F over multiplication must constitute an abelian group, and the next property is distribution of multiplication over addition. Okay. So, if these three property hold, that means with respect to addition F must be an abelian group, with respect to multiplication the set excluding 0 in F must be an abelian group, and distribution of multiplication over addition, this property must hold. So, if these three property holds, then we say that F is a field. Let us see few examples based on this. Now, you see set of real numbers. Now, if you see set of real numbers and which is a binary operation, the first binary operation is usual addition and the next binary operation usual multiplication. Now, usual addition forms an abelian group for this set of real numbers, we have already seen. Okay. And if you exclude 0 from the set of real numbers, it will also forms an abelian group with respect to multiplication, and dot and multiplication distribute over addition also from left and from right also. So, we say that the set of real numbers with the usual addition and multiplication forms a field, is a field. Okay. Now, you see the set of complex numbers. Okay. Usual addition and usual multiplication, again the two binary operations are usual addition, usual multiplication. Now, you see the set of complex numbers, under usual addition constitute a abelian group. This we can easily see all the 4 properties. I mean it is a binary operation, addition is a binary operation, number 1, associativity, identity is 0 and the inverse is minus A of any A in C. So, and also A into B is equals to B into A for all elements A, B and C. So, it constitute a abelian group over usual multiplication, and if you exclude 0 from this C, then this will also constitute abelian group over usual multiplication. Okay. And multiplication satisfies distributive over addition also. So, it will constitute a field. Similarly, the third example, a set of rational numbers with a usual addition, usual multiplication is also a field. Now, see some examples which are not fields. suppose we are considering set of integers. Now, set of integers under usual addition, set of integers under usual addition constitute a abelian group, it is true, but under usual multiplication it does not form a group even, because if you take a element say 2 in z, so its inverse is multiplicative inverse is 1 by 2 which is not in z. So, this set of integers does not constitute group under multiplication, so it will not constitute a field. Similarly, if you take a Euclidean space say R2, R2 is all xy such that xy are in R. Okay. Now, under usual addition it again constitute a group, I mean abelian group in fact, because associativity property hold, identity is 0 comma 0 and inverse of any a comma b in R2 is minus a minus b which is also in R2. But if you take the if you see with respect to multiplication excluding 0 0, there are other elements say 1 comma 0 which are in R2, but its inverse does not exist. Hence, this R2 under usual multiplication does not constitute a group, so it is not a field. Now, come to matrices. So, we define group and field because we want to define matrices over a field K. Matrices are always defined over a field. Okay. So, that is why we first clear out that what do you mean by a field. Okay. Now, we define matrices. What do you mean by matrices? So, a matrix A over a field K, K may be any field, is a rectangular array of scalars usually represented in the following form. So, any matrix A can be represented as a rectangular form A11, A12, A13 up to A1n, and similarly AM1, M2 and Amn. So, if we take any Aij, Aij means ijth entry of this matrix A. Ijth entry means the element in the ith row and in the jth column. Suppose we are talking about A22, A22 is the element in the second row and in the second column. If we are talking about A2n, A2n means element in the second row and nth column. Okay. So, we denote a matrix by simply writing A equals to Aij, and this denote the order of the matrix. The order of the matrix is m into n, because number of rows here are m and number of columns here are n. So, the order of the matrix is m cross n, rows into columns. So, these are general representation of a matrix A, which is Aij means any element ijth, I is varying from 1 to m and j is varying from 1 to n. These are some simple properties of a matrices. We already know these things, that A plus 0 equals to, they are 0 matrix, okay, because 0 plus A equal to A minus A equal to 0, A plus B associativity property hold with respect to addition and multiplication, then it distribute dot distribute over addition, because it satisfy this property. A plus B equals to B plus A. These three are the very basic properties, this already holds in matrices. Now, properties of transpose. What do you mean by transpose? Transpose means you interchange rows and columns. Okay. Suppose A is any matrix which is suppose 1, 2, 3, 4, 5, 6. It is having 3 rows and 2 columns, and you want to find out A transpose. So, A transpose means you simply convert rows into columns, that is 1, 2, 3, 4, 5, 6. So, this is the way of writing A transpose, means you interchange rows by columns, first row in first column, second row in second column, third row in third column. Okay. So, these property hold for transpose also. A plus minus B whole transpose is A transpose plus minus B transpose. K into A whole transpose is K times A transpose, where K is any scalar. Transpose of transpose is itself, and if A into B is defined, then A into B whole transpose is equal to B transpose into A transpose. Now, adjoint of a matrix. Let A be a n cross n matrix, a square matrix of order n cross n. Then how to find adjoint first? You first find cofactor of a element aij, which is given by minus 1 raised to power minus 1 raised to power I plus j mij, where mij is a minor of aij. Okay. This we already know. Adjoint of A is simply you make the matrix of cofactors and then take the transpose, that will be the adjoint of a matrix A, and we also denote it by this expression adjoint of A. Then the third property is A into adjoint of A is equal to adjoint of A into A is equal to determinant of A times identity matrix of the same order, of course, n cross n. Then determinant of adjoint of A is determinant of A raised to power n minus 1. This is very easy to prove, you can simply see here. As you have seen that A into adjoint of A is equals to adjoint of A into A equal to determinant of A times identity. So, you take this is A into adjoint of A is equal to determinant of A times identity. Now, you take determinant both the sides. Okay. Now, this is A into B. The determinant of A into B is equal to determinant of A into determinant of B, and also determinant of K into A, where K is any scalar and A is a matrix of order n cross n, is simply equal to K raised to power n determinant of A, if A is a matrix of order n cross n. Okay. Because this K is multiplied with all the elements of A, and when you take the determinant, you can take the common from each row, first row, second row up to nth row. So, K raised to power n will be common and then it will be determinant of A. So, here determinant of A works as K because it is a scalar, it is a scalar quantity, and I is a matrix of order n cross n. So, it is determinant of A raised to power n and determinant of I. Determinant of I is 1, so it is determinant of I. So, this implies determinant of adjoint of A is simply determinant of A raised to power n minus 1. Also, we know this thing that if matrix is invertible, then inverse exists and inverse is given by adjoint of A upon determinant of A. Now, this is a very simple problem. Let us see just to illustrate few properties of matrices. Okay. Now, here determinant of A is 3 and A is a matrix of 2 cross 2 order. If you want to find out determinant of 2A, so it will be simply, because we know that determinant of K into A is equal to K raised to power n times determinant of A, if A is a matrix of order n cross n. Here matrix of order 2 cross 2 and K is 2. So, it is 2 raised to power 2 determinant of A, which is 4 into 3, which is 12. If you want to find out a determinant of adjoint of A, it is simply determinant of A raised to power n minus 1, here n is 2, okay, and determinant of A is 3. So, 3 raised to power 1, which is 3. If you want to find out determinant of adjoint of 2A transpose, so it is simply determinant of 2A transpose whole raised to power 2 minus 1, which is determinant of 2A transpose, which is equals to 2 raised to power n which is 2 into determinant of A transpose. Determinant of A transpose and A are same. So, it is determinant of A, which is equals to 4 into 3, which is 12. Okay. So, in this way we can simply solve this problem. Okay. So, these are some special type of matrices. Row matrix is a matrix is said to be a row matrix if it consists only one row. Column matrix, a matrix said to be a column matrix if it consists of only one column. Diagonal matrix or square matrix is said to be diagonal if its non-diagonal entries are all 0, that is a diagonal matrix. A scalar matrix, a diagonal matrix said to be scalar if its all diagonal elements are same, say K. Symmetric matrix means a matrix A is said to be symmetric if A transpose A equal to A, that is Aij equals to Aji for all ij. We will discuss more about symmetric and skew symmetric matrix in detail later on. Okay. Skew symmetric matrix, a matrix A is said to be skew symmetric if A transpose is equal to minus A, that is Aij equal to minus Aji for all I and j, and also the diagonal element of skew symmetric matrix are 0. Now, what are elementary row operations? So, first we are talking about matrices over the field F or over the field K. So, these scalars whatever we are talking about comes from the field. If the field is a set of real numbers, then the scalars will be a set real, and if we are talking about the set of complex number, the scalars come from the set of complex numbers. Okay. Now, what are elementary row operations? Let us see. There are 3 elementary row operations on an M cross N matrix A over the field F. What are they? Number 1, multiplication of any row of A by a non-zero scalar C. You see, if you take any row Rj of a matrix A and you multiply that row by a non-zero scalar C, then this is the first elementary row operation which we can apply on a matrix A. The second elementary row operation is replacement of the rth row of A by row plus C times S row, where C is any scalar and R is not equal to S. That means, you take any rth row, okay, and you replace this rth row by the rth row plus C times some other sth row, then this is a second elementary row operation on any matrix A, and you can always interchange any 2 rows. You can interchange ith row with jth or jth with by ith, I is not equal to j. So, these are the 3 basic elementary row operations. Number 1 is you can multiply an row by any non-zero scalar C. Then you can always, for any row, you can always take row plus C times some other row Rs, and you can always interchange any 2 rows of A. So, these are the 3 elementary row operations. Now, let us discuss this by an example. Now, first thing is, let us discuss this also first. Definition: if A and B are M cross N matrices over the field F, we say that B is row equivalent to A if B can be obtained from A by the finite sequence of elementary row operations. You see, you have a matrix A and you apply some elementary row operations on that matrix and you get a new matrix B, then we say that the matrix B is row equivalent to A. Okay. Now, you take, we discuss this example. Okay. You take A, let us suppose you take A equal to 1 2 3 minus 1 0 2 2 4 4. Now, using elementary row operations, transform A into identity matrix. Suppose we have to apply elementary row operation on this matrix A and we have to convert this matrix into an identity matrix. So, how can we convert this? So, let us see. Here is a solution. Let us discuss a solution first. So, this is matrix A. Okay, this is a matrix A. So, in the identity, we have to take this element as 1, the first element as 1, and in that column, all the elements must be 0. Okay. Similarly for the second element and for the third element, I mean in diagonal. Now, to make 0 here, which elementary row operation we will apply? To make 0 here, we will take this row R2 and we add with R1, because minus 1 plus 1 will become 0 here. So, we make first elementary row operation in R2 row and we replace R2 by R2 plus R1. Okay. Now, this minus 1 plus 1 is 0, 0 plus 2 is 2, 2 plus 3 is 5. So, this is the first elementary row operation which we have applied in this matrix. Now, the next is we have to make 0 here, because we want to make identity here. Okay. Now, to make 0 here, we have to take the third row and we have to subtract 2 times the first row. I mean, we have to replace the third row by R 3 minus 2 times R 1, then it will become 0. 2 minus 2 times 1 becomes 0. So, this minus 2 times this 0, this minus 2 times this becomes 0, this minus 2 times this become minus 2. Now we have to make 1 here to make identity. So, replace this row by 1 by 2 this row, I mean replace R 2 by 1 by 2 R 2, because you want to make 1 here. Okay. So, you replace R 2 by 1 by 2 R 2, we get another matrix which is this 1 2 3 0 1 5 by 2, because we divide by 2 here, and 0 0 minus 2. Now, we want to make 1 here. Okay. So, we divide this by minus 2. If you divide this by minus 2 or replace this row by minus 1 by 2 times R 3, then it is 1 2 3 0 1 5 by 2 0 0 1. Now, you have to make 0 here and 0 here to complete the identity matrix. To make 0 here with the help of this row, you simply take this row 1 and you subtract it with twice of row 2. That means, in the row 1 you apply the elementary operation R 1 minus 2 times R 2. So, this minus 2 times this is 1, this minus 2 times this is 0, this minus 2 times this is minus 2, and all other elements remain the same. Now, you have to make 0 here. So, to make 0 here, we take the help of this 1. So, this plus 2 times this, I mean R 1, you replace R 1 by R 1 plus 2 times R 3. So, this plus 2 times this is 1, this plus 2 times this is 0, this plus 2 times this is 0, and the other elements remain the same. Now, you want to make 0 here to complete the identity matrix. So, this minus 5 by 2 times this row, I mean R 2, you replace R 2 by R 2 minus 5 by 2 times R 3. So, this will be the identity matrix. So, we have applied a series of elementary operations to convert matrix A into an identity matrix. Okay. Now, if you talk about this matrix A, this matrix, so this matrix is obtained from the matrix A by 2 elementary operations. So, we can say that this matrix is a row equivalent matrix to A, or in fact we can say any matrix up to here are the row equivalent forms of the matrix A, because they are obtained by applying some elementary row operation on the matrix A. Okay. Now, let us discuss these examples. Discuss first example. Suppose we discuss to convert this into an identity matrix by applying elementary row operation. Okay. So, what is the matrix? You see, matrix is 2 minus 1 0, it is 1 minus 1 2, it is minus 1 0 1, it is a matrix. Now, by applying elementary row operation, you want to transform this matrix into an identity matrix. So, how you will proceed? In the first column, you see if there is any 1, I mean any element 1, then you interchange those rows first. Okay. So, first what you do, you take you replace R 1 and R 2, you interchange R 1 and R 2. So, this is 1 minus 1 2, it is 2 minus 1 0, it is minus 1 0 1. To make our calculation easy, the other way out is you divide it by 2 and then apply the elementary row operations. Okay. Now, you want to make 0 here with the help of this. So, to make 0 here with the help of this, you replace R 2 by R 2 minus 2 times R 1, then only it will become 0. So, it is 1 minus 1 2, it is 0, this minus 2 times this is 1, this minus 2 times this is minus 4, it is minus 1 0 1. Now, you want to make 0 here with the help of this. So, replace R 3 by R 3 plus R 1. So, this will be 1 minus 1 2, it will be 0 1 minus 4, it will be 0 minus 1 3. Now, this is already 1, you want to make 0 here because you have to complete identity matrix. So, again you apply elementary row operation, you will replace R 3 by R 3 plus R 2. So, this will be 1 minus 1 2, it will be 0 1 minus 4, it will be 0 0 minus 1. Now, it is minus 1, you have to make 1 here. So, you multiply this by minus 1, you replace R 3 by minus of R 3. So, this is 1 minus 1 2, 0 1 minus 4, 0 0 1. Now, you want to make 0 here with the help of this. So, you replace R 2 R 1 by, you replace R 1 by R 1 plus R 2. So, it is 1 0 minus 2, it is 0 1 minus 4, it is 0 0 1. Okay. Now, you want to make 0 here with the help of this. So, this plus 2 times this. So, in R 1 you take R 1 plus 2 times R 3. So, it is 1 0 minus 2, 0 1 minus 4, 0, okay, it is 0 0. So, this will be simply 0 and it is 0 1. Now, you want to make 0 here with the help of this. So, this plus 4 times this will give you the identity matrix, that means you replace R 2 by R 2 plus 4 times R 3. So, it will be an identity matrix now. So, these are the elementary operations which we apply to convert this matrix A into an identity matrix. Similarly, we can proceed for the second problem. So, thank you very much.